Hey guys, today's lesson is all about titrations. Now, if we were back in school right now, we would be doing a titration lab. Unfortunately, it's not something that we can do at home, but you will get to do one in Chem 30 in all likelihood. And if you take Chem in university, you'll probably do one there too. Um, but we are going to still learn about how to do them. It is still really important. This is a super long lesson though. I think it's like my longest lesson in any subject. So I am going to be breaking it into at least two video lessons. So just so you know. Okay, so like I said, this lesson is about titrations. Honestly, most of this titration stuff is going to be like all calculations that you've done already. There'll be some new terminology, and we'll be combining calculations in a way that you might not have done before, but none of the calculations are going to be new to you. So we'll start by going over some of the terminology. We'll talk about the difference between endpoint and equivalence point. We'll briefly look at some of the steps of performing a titration, but that's not going to be as important since you won't get to do one this year. Then we're going to look at how to calculate the concentration of an analyte, which is just a normal solution stoichiometry type problem. Then we're going to be using that information to calculate the pH of both strong acids and bases as well as weak acids and bases, where you're given a Ka or Kb value. And then we also are going to look at calculating the volume of titrant used, which is also a solution stoichiometry problem. And then the last thing we're going to be looking at is reading titration curves and picking indicators. So just some terminology to get you guys started. A titration is a process used to determine the concentration of an acid or base in a really controlled neutralization reaction. When you're doing a titration, you literally add like 1 or 2 drops of either your acid or your base to either your acid or your base in a neutralization reaction. So it's incredibly controlled and measured. The titrant is the acid or base that you know the concentration of that's being added to the solution with the unknown concentration. The analyte is the acid or base that you don't know the concentration of, and you're going to be adding the titrant to the analyte. The equivalence point is the point in the titration where the moles of the titrant is equal to the moles of the analyte. So essentially where the acid and base moles are equal. The end point is when you have a sudden change in pH as well as indicator color. It should match the equivalence point if you've picked a good indicator. But the equivalence point is like a theoretical point that you would calculate using like mole ratios and looking at titration curves. The end point is when you can like physically see a color change that has happened because of a pH change. These are the different tools that we use during a titration. So this big, tall glass rod, it's like super long and skinny, is the burette. That would be filled with your titrant. Then you have at the bottom of the burette here something called the stopcock, which you turn to either allow the titrant to flow or to stop the flow of titrant. Then you have the stand and burette clamp, which just holds the burette above the flask. You've got your Erlenmeyer flask down here at the bottom, which would have your analyte in it. If you're really fancy, you would have a little magnetic stirrer set up to constantly stir your analyte solution. We're not that fancy at our school, so you just have to have someone like physically gently mixing the analyte all the time. And then you would also have an indicator, a pH indicator, inside the flask in the solution of analyte. So you would start with a very precise measurement of the volume of analyte, and obviously record that. That's going to be inside of your Erlenmeyer flask. Then you have the burette. You're going to fill your burette with your titrant, let out a little bit of it just to make sure there's no air bubbles, and then record the volume of titrant that you have. Then you'll put a couple drops of an indicator into your analyte, and then you'll just, a few drops at a time, add the titrant into the analyte, stirring the analyte constantly until that analyte solution becomes, well, if we were doing our titration, we'd be looking for a light pink, but we're going to talk later about how you decide which indicator to use. So if you were using a different indicator, you'd be looking for a different color. But in the example that we always do, you're looking for a light pink color. Usually what would happen is like the titrant would drop into the analyte and it would show up pink, but then as it dispersed, it would become neutralized and it would go back clear again. And eventually you'll get to the point where it stops becoming clear and just stays as a very, very light pink. If it goes to a darker pink, you have over titrated and gone past your endpoint. Once you have reached the endpoint, you record how much of your titrant you have used. That's really important when you're doing your calculations. And you should always run each titration 3 times, do 3 trials, in order to make sure your results are accurate. So the first and most common type of titration calculation you need to be able to do is finding an unknown concentration. Almost always it is the analyte that you don't know the concentration of. So of course you start with your balanced chemical equation. With titrations, it's always a neutralization reaction. Then if it's not given to you, you figure out what the volume of titrant used was. Sometimes instead of just saying like 12 milliliters of titrant was used, it might say like you started off with 40 milliliters and you ended up with 28, which obviously means that you've used 12. Then you're going to use C equals N over V to calculate the moles of your titrant, mole ratio to figure out the moles of your analyte. You already know the volume of your analyte, so back to C equals N over V for the concentration of your analyte. So again, it is just a simple solution stoichiometry problem. So I'll leave this example for you guys to read over if you would like to. And then we will try the first one here and you guys can try the next 2. Okay, so the first question here, oops, sorry, I'm actually on the wrong slide. There we go. The first question here says we have 0.3 molar sodium hydroxide, so NaOH, titrated into, so added to carbonic acid. So H2CO3 is carbonic acid. It wants to know the concentration of the analyte. So we've got 35 milliliters of our carbonic acid. It's looking for the concentration. It also tells us that the reading on the burette went from 50 to 38. So if we just subtract those, which I should be able to do in my head, but I'm not, it's 12 milliliters. And so we're going to, of course, write the rest of our neutralization reaction. All neutralization reactions make water, and then our salt will be Na2CO3. So, of course, we have to balance this. We'll put a 2 there and a 2 there, and then it's balanced. So that's our first step. Make sure everything's balanced. Make sure we have both volume and concentration for one of our reactants, and then volume for the other one. Step 2, we're going to do C equals N over V for the reactant that we know both the volume and the concentration of. So our concentration is 0.3. Don't forget your volume must be in liters. So convert it to liters by dividing by 1,000, and then just multiply to solve for N. And you should get 0.0036 moles, and that is of the NaOH. Then we're going to set up a mole ratio between our sodium hydroxide and our carbonic acid, which will be a 2:1. I'll plug in my moles of my base that I just solved for, and then cross multiply and divide in order to figure out my moles of carbonic acid, which is 0.0018 moles. And then the last step is to just go back to C equals N over V, plug in our moles, plug in the volume, though don't forget to turn that into liters. And we get 0.05 molar as our concentration of carbonic acid. So that's your final answer. So try the next two and then come back for the answers. Okay, so for the second question, we have phosphoric acid reacting with lithium hydroxide. It'll make water and lithium phosphate. We have 0.2 molars and 21 milliliters of the acid, 15 milliliters, and an unknown concentration of our base. So we'll start with C equals N over V for our acid. Multiply and get 0.00042 moles of the acid. Set up a mole ratio between the two reactants. It's a 1:3 ratio. So we cross multiply and get 0.00126 moles of the lithium hydroxide. Plug that into C equals N over V and get 0.084 molars of the lithium hydroxide. Okay, and then for the final one, we have hydrofluoric acid reacting with calcium hydroxide to make water and calcium fluoride. We start with C equals N over V for the acid, since we have both the concentration and the volume, and you should get 0.00195 moles of the hydrofluoric acid. We set up a mole ratio between that and our base, which is a 2:1 ratio. Cross multiply and divide and get 0.000975 moles of calcium hydroxide. Plug that into C equals N over V using the volume of calcium hydroxide in liters and get 0.065 molar calcium hydroxide. Okay, next step, we're going to use that solution stoichiometries type stuff to figure out the pH of strong acids and bases. So usually the next step after finding the concentration of your analyte would be to find the pH of your analyte. In order to do that, you of course need to write either the ionization reaction if it's an acid or the dissociation reaction if it's a base. Then set up the mole ratio between your analyte and either the hydronium or hydroxide ions in order to calculate the concentration of those. And then you're going to use either the pH or pOH formula to calculate pH. So again, that's an example that you can look through of how that would work. Let's go through, we'll do number 1 together, and then you guys can try number 2 and 3 on your own. Okay, so for the first question, it's asking about the pH of the analytes from questions 2 and 3. So question 2, let me just get here. So this is what we've already done for that question. And that's where we figured out that the concentration of our lithium hydroxide, which is the analyte in this case, was 0.084. Our next step, if it asks us to find the pH of that, would be step 5, where we now write out our dissociation reaction, since it's a base, and then this is already balanced. And then our next step would be to set up a mole ratio between the analyte and the hydroxide ions, and the hydroxide ions, which in this case would be a 1:1 ratio. So if we plug in the 0.084 molars and then cross multiply, we end up with, running out of space here, we end up with x equals 0.084, which would be our concentration of hydroxide. Once we have that, then we can go to step 7, which would be our POH formula, so the negative log of the concentration of hydroxide. So the negative log of 0.084, which is 1.076. And then, of course, step 8, to find the pH, we just subtract that from 14. Which is 12.9-ish as our pH. Okay, so we've already done this in the previous chapter where we find pH. It works the exact same way. If we were to look at question number 3, again, we found that our calcium hydroxide had a concentration of 0.065. So once again, because it is a base, we have to take our calcium hydroxide and just dissociate it. Though in this case, in order to balance it, we need a 2 in front of our OH. Then we can set up our mole ratio between our analyte, which in this case is the base, and our hydroxide. So it is a 1:2 ratio this time. We'll plug in our concentration of our analyte and just cross multiply to get the concentration of hydroxide. So 0.13 molar is our concentration of hydroxide ions. Now that we know that, we can plug it into our POH, take the negative log of that, and get 0.886 as the POH, and then of course just subtract it from 14 to get 13.1 as the pH. Okay, so try the next 2 on your own and then come back to the answers. Okay, so for question number 2, you have potassium hydroxide reacting with sulfuric acid to make water and potassium sulfate. Because we're given the concentration and volume of our base, we're going to do C equals N over V with that, and we get 0.052 moles of our base. Then we set up a mole ratio between our base and our acid, which is a 2:1 ratio. And when you cross multiply and divide, you get 0.026 moles of our acid. Plug that into C equals N over V and get 1.3 molar sulfuric acid. Because our analyte in this case is an acid, we have to ionize it, so react it with water to make hydronium, and then in this case a sulfate ion. And then when we balance it, we end up with a 2 in front of the water and the hydronium. Set up a mole ratio between your acid and the hydronium ions, which is a 1:2 ratio. Plug in the concentration of your acid, cross multiply, and you get 2.6 molar as your concentration of hydronium ions. Because it is hydronium ions, you can plug it right into the pH formula. When we take the negative log of 2.6, you get negative 0.415 as your pH. Okay, and this last one, it isn't any more complicated than what we just did, but it is more steps, because this time it is asking you for the pH of both the analyte and the titrant. So we're going to start the same way. Start with our balanced chemical equation, nitric acid reacting with barium hydroxide to make water and barium nitrate. Balance it by putting some 2's in. And then we start with C equals N over V for the thing we have both the concentration and the volume for. And when we do that, you should get 0.0076 moles of the nitric acid. set up a mole ratio between that and your base. It's a 2-to-1 ratio. So when you cross multiply and divide, you should get 0.0038 moles of your barium hydroxide. Then you plug that into C equals N over V with our volume of barium hydroxide and get 0.126 repeating molar barium hydroxide as the concentration. Then because it's asking for the pH of both the titrant and the analyte, we are going to ionize our acid and dissociate our base and then make sure they're both balanced. The first one's already balanced. The second one, you have to put a 2 in front of the hydroxide. Then we are going to use those reactions to create mole ratios. So for our first reaction, for our acid, it is a 1-to-1 ratio between the acid and the hydronium ions. We're plugging in the concentration of the acid that we were actually given in the question, and then cross multiply, and you will get 0.4 molar as your concentration of hydronium ions. We do the same thing for our base. It is a 1-to-2 ratio between the base and the hydroxide ion. We plug in the concentration of the base that we just calculated, cross multiply, and get 0.253 repeating molar as the concentration of hydroxide ions. Then we are going to calculate the pH of our acid by just taking the negative log of the concentration of hydronium ions that we just solved for, and you should get a pH of 0.398 for your nitric acid. For our base, we have to do a pOH calculation, so we'll take the negative log of the concentration of hydroxide that we just solved for and get 0.596 as the pOH, and of course just subtract it from 14 to get the pH of our barium hydroxide, which is 13.4. Okay, the last thing we're going to be doing today is finding the pH of weak acids and bases using a titration. This time you will be given a Ka or Kb value, and so of course we're going to have to use that formula instead of our normal pH or pOH formula in order to calculate our pH or pOH. So we're going to start just like we have been doing with our balanced chemical equation. We'll do the C equals N over V for the titrant, mole ratio to find the moles of the analyte, and then back to C equals N over V for our concentration of our analyte. So that is just the normal solution stoichiometry stuff that we've been doing all along. And then you will find the concentration of either your hydronium or hydroxide ions, not by using the mole ratio this time, like you do with strong acids and bases, but instead by using either the Ka or Kb formula. Then you can plug those into your pH or pOH formulas. Okay, so here's an example again that you can look over. We'll do the first one here together, and then you guys can do the next two on your own. Okay, so for the first question, it says carbonic acid, which is H2CO3, is a weak acid with a Ka of 4.5 times 10 to the negative 7. Determine the pH from question 1. So in this case, we've already done the solution stoichiometry part. So you start with your balanced chemical equation, C equals N over V, mole ratio, back to C equals N over V. That is our concentration of the H2CO3, the carbonic acid. We're now going to use that concentration, and instead of plugging it into the mole ratio like we would if this was a strong acid or base, we're going to plug this into our Ka formula instead. So let's see what that would look like. So the Ka is 4.5 times 10 to the negative 7. On the top, we have our x squared, and then on the bottom, we have our concentration of our acid. which is what we've calculated, so the 0.05. Then, of course, we multiply by 0.05 on both sides. So 4.5 times 10 to the negative 7 times 0.05 is 2.3 times 10 to the negative 8. Okay, then of course I need to square root to get the x by itself. So these, whoopsies, square root of 2.3 times 10 to the negative 8 is 0.000152. So that is our concentration of H3O+, since this is an acid that we're dealing with, which means, that would have been step 5, step 6, we can just plug that into our pH formula. So we'll take the negative log of 0.000152 and we get a pH of 3.82. Okay, the second question is a reaction between lithium hydroxide and hydrosulfuric acid, or hydrogen sulfide. So of course we start by writing our balanced chemical equation, then we'll do C equals N over V for the thing we have both the concentration and volume for. That gives us 0.0165 moles of lithium hydroxide. Set up a mole ratio between that and our hydrogen sulfide, which is a 2-to-1 ratio. Cross multiply and divide and get 0.00825 moles of hydrogen sulfide. Plug that into C equals N over V and get 0.33 molar as our concentration of hydrogen sulfide. Once we have our concentration of hydrogen sulfide, we plug it into our Ka formula. So our Ka is equal to x squared over the concentration of our hydrogen sulfide. We multiply by that concentration and get 3.1 times 10 to the negative 8, and then square root to get 0.000176 molar as our x, which is our concentration of hydronium ions. We can then plug that into our pH formula to get a pH of 3.75. Okay, the next equation is a little bit different because, as you can see here, our base, because it's a weak base, doesn't have an OH in it. So we're not going to be making water and a salt the way that we normally would. We're just kind of combining everything here. And I'll show you where to review that kind of neutralization reaction once we're done this. But anyway, we're going to balance that by putting a 2 in front of our ammonia. Then we start with our C equals N over V for the thing that we have, the C and the V for. And when you do that, you'll get 0.0065 moles of sulfuric acid. Set up your mole ratio between that and the ammonia, which is a 1-to-2 ratio. Cross multiply and get 0.013 moles of the ammonia. Plug that into C equals N over V and get 0.43 repeating molar as your concentration of ammonia. Then, of course, you can plug that into the Kb formula. So plug in your Kb, plug in your concentration of ammonia, multiply and get 7.8 times 10 to the negative 6 equals x squared, square root, and get 0.0028 molar, which is your concentration of hydroxide ions. Because we're dealing with a base this time, you plug that into the POH formula and get 2.55, subtract it from 14 and get 11.45. Okay, and for those of you that are wondering how I came up with that reaction involving ammonia, just take a look at this slide and the next one. As you can see, neutralizations with a weak base don't follow the normal pattern of an acid plus a base makes a water and a salt. Instead, as you can see here, we just have the acid and the base making a combination of the base with the acid. And you can see an example of that. Well, down at the bottom here, it's explaining why that works. But on the next page at the bottom there, you can see an example of what that would look like. So that is what you should be using. Really, the only time we do that is when we're dealing with ammonia as the base in one of these neutralization reactions. Okay, if you have any other questions, please let me know. We will finish the rest of this titration lesson tomorrow.